Hello everyone. We were discussing the gaseous law in thermodynamics chapter, and in the previous lecture we did things like first law of thermodynamics, and we discussed what is basically meant by internal energy. We learned various sign conventions related to the first law of thermodynamics, and we learned the two specific heats of the gas. In this lecture we will discuss some questions based on them, so as you can get more insight into how to use these quantities and how to practically use the equation, the first law of thermodynamics, and how to solve various questions based on them. So let's begin with the first question, which says that 1 mole of a gas, 1 mole of oxygen specifically, is heated at constant pressure from 0 degree Celsius. What must be the quantity of heat that should be supplied to the gas for the temperature to be doubled? Okay, and if the heat is applied at constant volume, what will be the final temperature? Okay, so basically that's the question. That 1 mole of oxygen is heated at constant pressure at 0 degree Celsius, such that the temperature gets doubled. So find what is the heat energy supplied to the gas, and if the same amount of heat is supplied at the constant volume, how much temperature it would attain. First of all, it must be clear to you that when you would fix the volume, the same amount of heat, all the heat that you supply gets transferred into the internal energy, so it would raise the temperature more. So obviously the temperature would be higher than the case in the first one. Okay. So first of all, in the first case you are doing constant pressure, so the heat supplied would be NCP delta T. Now the only requirement over here is you have to find the final temperature. Okay, that is delta T. Now it says that the temperature is doubled. Temperature 1 is nothing but 273 Kelvin, and the final temperature, that is TF, is given by 2 times 273, that is nothing but 546 Kelvin. So delta T is 273 Kelvin. The moles are also given, that is 1 mole of a gas. Cp we have to think, it is O2, that is oxygen, that is a diatomic molecule. We know that for a diatomic gas we have the Cp as 7R by 2 because it has 5 degrees of freedom, so Cv is nothing but 5R by 2 and Cp is 7R by 2. Okay, we plug in these values and the delta T is 273 Kelvin. To get the value as 7 by 2 into 8.3, the very important thing over here is the value of R. Most of you are familiar with the value 0.0821, but that is not the correct value over here, because that is the value when the units are in atm. The pressure is in atm, the moles in the number of moles is in the quantity of moles, and the temperature is in Kelvin, and the volume is in liters. But here we are dealing with the SI units, so you have to use the SI unit value of R, that is 8.3 into 273. That gives us 7930.6 joules. Okay, so this is the amount of heat energy that must be supplied when the pressure is constant in order to double the temperature. Now if we supply the same amount of heat in the case of constant volume, so delta Q is equal to delta U plus W. So work over here is 0. So delta Q that is supplied is 7930.6. It changes the internal energy that is given by NCV delta T. which is nothing but N is 1 over here, Cv is 5R by 2 into T. So that is, if we break it down into the same form as it was here, so it would be 7 by 2 into 8.3, that was the value for R, into 273 upon upon 5 into 8.3 into 2. Okay, so 8.3 would get cancelled out, 2 and 2 would cancel out, and it would give us 7 by 5 into 273. So that you can calculate. It is nothing but 7 into 3 is 21, 2, 51, 5, 19 upon 5. Okay, so this would give us 382.2 degree Kelvin. So the final temperature would be nothing but 273 plus 382.2, which is 655.2 Kelvin. So this is the final temperature that would be attained if the same amount of heat is supplied at constant volume. So in this question, we use nothing but the two basic concepts, that delta Q under constant pressure is given by NCP delta T, and the Cp for the diatomic gas is given by 7R by 2. And the under constant volume, delta Q is equal to delta U. So delta Q is obtained from the previous process and it is put into the value for NCV delta T, and we find the change in the temperature. Okay. So using that change in the temperature, we can find the final temperature attained by the gas. Okay. So let's try and do another question that is based on a different concept. Okay. So the question is, when water is boiled, under pressure of 2 atm, a heat of vaporization a very important concept in this chapter is keeping an eye on the units, because a slight change in the units can do you hell in the question. You might have all the concepts, you might do all the question correctly, but if the units are wrong, you get it all wrong. Okay, so the heat of vaporization over here is 2.20 into 10 raised to power 6 joules per kg, and boiling point (120°C). Okay. At this pressure, 1 kg of water has a volume 10 raised to power minus 3 meter cube, and 1 kg of steam has volume equals to 0.824 meter cube. What you have to find is basically compute the work done when 1 kg of gas or 1 kg of steam is formed at this temperature. The second thing you are required to find is compute the delta U. Okay, change in the internal energy. So let's try and first of all understand what the question says. It says that water is going through a process, that is of boiling. Okay. Pressure of 2 atm is present on the water, and a heat of vaporization is this much. That is the specific heat for vaporizing the water, and the boiling temperature is given as 120°C. Okay, so basically it is the process of conversion of water into vapors. At this pressure, the 1 kg of water has a volume this, and 1 kg of steam has volume this. Okay, So one thing you should understand that first of all it is a constant pressure scenario. Okay. So the work done by 1 kg of steam is the work done by the gas, which is given by P into dV is equal to dW. So basically the work done would be P into delta V. Okay, so the change in the volume is given by, as we know that the volume of water is this much and volume of steam is this much. So obviously the water has been converted into the steam. So the change in the volume is final minus initial, which is given by P into 0.824 minus 0.001, that is 0.823 into pressure. Okay. Another very important concept over here is that the value of the pressure over here. Pressure is given in atms. You have to convert it into joules or say Newton per meter square. Okay. So the pressure over here was 2 atm. 2 into 1 atm is 1.013 into 10 raised to power 5 Newton per meter square. And it is multiplied with 823 volume, that is meter cube. So meter gives this, and Newton into meter gives us a joule, which says that 2 into 1.013 into 0.823 into 10 raised to power 5 joules, which is nothing but 166.74 into 10 raised to power 3 joules. So this much work is basically done. So the important thing over here was to realize that it is a constant pressure scenario and the change in the volume, and the very important fact that there is a anomaly in the units. So you have to keep in mind to form the correct units. Okay. So the second question was, what is the increase in the internal energy? Okay. Internal energy, as you know that delta Q gives us delta U plus W. So change in internal energy can be very easily found by the change in the total energy and the work done. Correct? So total energy supplied from outside minus the work done gives us the change in the internal energy. So the amount of heat given from outside was the heat of vaporization and into the mass. The mass is given to be 1 kg only. So this is 1 into the heat of vaporization, 1 kg into heat of vaporization, that was 2.20 into 10 raised to power 6 joules per kg. So it gives us the total energy supplied from outside, that is 2.20 into 10 raised to power 6 minus the work done by the gas, that is 0.16674 into 10 raised to power 6, which gives us, if you subtract them, it gives us 2.00326 into 10 raised to power 6 joules. That is the amount of change in internal energy. Okay. So this was a very easy question only, but the language might have made you think that it is a complex question. The easy concepts that were applied over here was work is equal to P into dV, P into delta V in the case of constant pressure, and the change in internal energy can be found by the total heat supplied from outside minus the work done. Okay. So these two, the last two questions were completely on different concepts. The next question as well. So let's try and do the next question, which says that there is a gas, there is a system for which you are given the PV curve. Okay. So the PV curve shows you some processes. The gas is taken from one state to another. The gas is first at A state, then it goes to F state through this process. It comes from B to F from this process, from B to I from this process, and from F to I it comes from this process, and A to I from this process. Okay. So this is basically the graph shown by the PV curve. Okay. So the system is taken from I to state F. Okay, from I to F it is taken. Along the path IA F. So the one wave you are going from I to F is like this. Okay, and you found that the delta Q value was 50 calories and the work you did was 20 calories. Okay, along the path then you went through the path IBF. You found the value as delta Q equals to 36 calories. This is for IBF and this is from IAF. Okay, so you try to go from one state to another by two different processes. Now, given this data, you have to find that what is delta W for path IBF. Now, as we know in the PV curve, the volume or the work done by the gas is nothing but the area under the PV curve. So, if we say that in the first process, that is from IAF, the work done was 20 calories, the area under the curve was 20 calories. Okay, so that is this whole box plus this bottom area gave you the 20 calories. Or we could say that delta Q is equal to delta U plus W for IAF. In that case, we found 50 is equal to delta U, we don't know, sorry, I wrote delta over here, it shouldn't be written, plus 20. So delta U was nothing but 30 calories for the IAF process. Now we know that the internal energy change is dependent on just the initial and the final state. So whichever process you might go, the change in the internal energy would be the same. Okay, so if you go by IBF process, delta Q is equal to delta U plus W for IBF as well. For IBF, you know that the delta U is nothing but 36 and the internal energy would be same as the IAF plus work. So work is nothing but 6 calories that you had to do going from IBF process. Now, as I said, the value for the work of the first IAF was this whole box plus this bottom area, right? And for IBF, it was just the bottom area. So the area of the bottom one is 6 calories. We found this as 6 calories. And the total work by IAF was the sum of this bottom area and the area of this rectangle. So we found the area of the rectangle as 14 calories. So, okay. Now we are saying that the second question asks us if delta W was minus 13 calories for Fi. The work is negative because you have to think that the volume is decreasing. First the volume was somewhat higher over here, say let's 10 liters, let's suppose, and here it became 2 liters. So obviously the volume is increasing. So work done is pressure into volume. So if the volume increases, the total work done also is negative. So that was for in general. So we are given that delta W is minus 13 calories for curved Fi. What is the delta Q for this path? You have to find. So delta Q for this path would also be delta U plus work. Delta U know that it is always same initial and the final only dependent on them. So it would also be 30 over here minus 13. So it would be nothing but 17 calories. Then the third question asks us, taking the internal energy at the state I as 10 Kelvin at 10 calories, what is UF? As we know that the change in the internal energy depends on only on the final state and the initial state. So delta U is nothing but U final minus U initial, and we know that it is nothing but 30 calories as we are given or we found in the first part, right? So UF minus 10 is nothing but 30. So final internal energy is nothing but 40 calories, right? So the last part of this question says that given the internal energy at B is 22 calories, right? What is delta Q for the process IB and for the process BF? Okay, so what we are dealing is over here. It says that we have found the value for internal energy at B. What is the work done if we go from I to B and B to F? So basically it has split the IBF process into two parts, from I to B and B to F. Okay, so let's try to find out what is the heat required for the process IB and BF. So we can say that delta Q is nothing but delta U plus work, correct? So delta Q, this is for the process IB, let's suppose. Okay, and delta Q is also equals to delta U plus W for the process BF, correct? We can say that first of all the work done by IB in the IB process is nothing but the area under this line, which is same as the work done by the IBF process, correct? So this would be nothing but delta Q is equal to delta U plus work IBF, that was given by 6 in the case of IB. And as you know that delta Q is U final minus U initial, so that is UB minus UI plus 6, and UB is given to be 22 and UI is given to be 10 plus 6, that gives us 18 calories for the IB process. That is the amount of heat required. Okay, now for the process BF. For BF you have no change in volume at all because it is a straight line at a constant volume. So there is no work at all done in this process. So we can directly put this work done as 0 over here. So delta Q would be nothing but delta U. So it would be nothing but the final state minus the initial state. So that would be U of F minus U of I. So that is given to us, U of F minus U of B. We are given that UF is nothing but 40 calories. 40 minus B is 22. That is 18 calories. So in this question, we basically use the each and every concept of PV curve. We tried to first of all see that the PV curve denotes various kinds of processes. We calibrated it with the first law of thermodynamics multiple times. Okay, so from the given equations, we tried to find out the work done first by the graph, that is the area under the curve. As we knew that IAF, the area under the curve would be the rectangle plus the area under the rectangle, right? And for the process IBF, it would be just the area under the rectangle. So the common part is under the rectangle and the separable part is of the rectangle, right? So in the first process, we find the area under the rectangle and the total area we were given to us. That was the work for the IAF was given to us. So we found the area for the rectangle part as well. That is 14 and 6 respectively. Okay. So by applying it multiple times, the formula delta Q is equal to delta U plus W for various processes, we made the use of the very important property that delta U is a state function. That is, if you have found it through any process between one initial and the final point, you can use it in any other equation as well, right? And similarly, the value for delta Q, it is also dependent on the final and the initial state. And like it was written over here, that for some locations, you can very well define the internal energy. That what I taught you, that it is a state function. The state functions help or enables you to write these kinds of equations. Otherwise, for work, you can't write like these. So, and the last part, we split the process, a given process, into two parts. So for each and every mark in the process, or smallest process possible in the graph, you can define the delta Q, delta U, and the work done. Okay. So there was a tough question. It would have been a tough question if we had to find directly the area under this curve. Okay. That was the question in the B part, that you have to find, you are given the work W of minus 13 of the curved path Fi. If you had to integrate it, it would have been a tough question, but because you had to just use the other informations, like you knew the delta Q and the delta U, you can directly find the value for W. So in each and every case, you don't have to integrate all the stuff and get the values. You have to see that, yes, there are certain state functions available. You can use them in order to find the specific values. So in this lecture, we discussed more or less all the concepts we have learned till now. In the first, related to the first law of thermodynamics, we learned that delta Q is nothing but NCP delta T in the case of constant pressure. We use that in the question, along with, we understood the fact that if the same amount of energy is given in constant pressure as well as constant volume, the temperature raise would be more in the constant volume case. Then we learned in the second question, we discussed the very basic meaning of work, that is PdV, right? And we made the use of that in the question, along with collaborated with the first law of thermodynamics. Then the third question was the most important question, which is a very familiar type of question, which has a PV curve and the concepts based on that. So in the next lecture, we will discuss various types of processes, like the isothermal process, adiabatic process, and various other types of processes, and the equations governing them, and try to find the work for them, as well as the change in the internal energy and other stuff. So that's all for today. Thank you.